So to get started, we're going to jump into chapter 2, as I said, for persons who are joining us. And I just want to start off by just going over some basic ways to represent what we refer to as organic molecules, right? So if you guys remember from Gen Chem, you guys learned about Lewis structure. If you remember, the Lewis structure was one in which you draw out all the carbons, the oxygen, the hydrogens, and you put a line that connects the different atoms together. So that's pretty much seen a full spectrum. If the atoms have lone pairs, you want to include the lone pairs. So that's pretty much one way to represent an organic compound. Another way to represent an organic compound is what's referred to as a partially condensed structure. And what do I mean by that? So for partially condensed, it means that you don't try to draw everything. We know that you normally have 3 hydrogens attached to that N carbon, so it's kind of abbreviated as like CH3 for the terminal carbons. And then for like, the heteroatom like oxygen, that always has a hydrogen, so let's abbreviate that as OH. And that works beautiful for small molecules. There's another way we could also write organic structures, and that's referred to as the condensed structure. That's where we just write we're just almost writing something similar to the molecular formula, but not as condensed. But we show that in parentheses, there are what's referred to 2 methyl groups that attach to the central carbon, and then that central carbon is attached to a hydroxyl group, and that's your condensed version. And then we could even make it even more simpler, where we have what's referred to as the molecular formula. So the molecular formula just gives a number of the different atoms, like 3 carbons, 8 hydrogens, 1 oxygen, and that's different ways that we can represent organic molecules. All right, so this works well when we're drawing small molecules, but for the molecules that I've showed you prior in the previous slides, where they're large and there are more atoms, we have to find a faster way of representing these molecules. And that's what I'm going to show you how to do. All right. If we look at the structure we have above, believe it or not, this structure is the structure of isopropanol. And you guys know what isopropanol is, right? It's used as rubbing alcohol. There are, believe it or not, what we call 3 isomers or 3 constitutional isomers of isopropanol. And the term constitutional isomers just means that they have the same molecular formula, but the way the atoms are connected are slightly different. That's all it means, right? So for isopropanol, we could draw 3 different structures. So we could have one where we take the hydroxyl functional group and just kind of move it over to the next carbon to the right, and move the hydrogen over to the next side. So we have what's referred to as propanol in the middle here. And then a third example is where we could, what if we take the oxygen and stick it right in between carbons 1 and 2? That's also a third constitutional isomer. How do I draw isopropanol? So you know that you put your carbon there, you attach to another carbon. One thing we know about carbon is it's tetravalent, right? So the term tetravalent means it's always bonded to 4 different atoms, right? So if I have a carbon, I make sure it's always attached to 4 different groups. So this is what I'll do. For every carbon, make sure it has 4 bonds attached to it, right? That's step 1. And then for oxygen, we know oxygen is divalent. So for oxygen, we'll just put a circle here, stick a line up there, and it means that oxygen is always bonded to 2 groups. We know that the lone pairs, there are 2 lone pairs in oxygen, so we put 2 a pair of lone pairs, 2 lone pairs on the oxygen. And then for hydrogen, we know that hydrogen is monovalent, so hydrogen only has 1 bond, right? This only bond to 1 other atom. We can stick the rest as shown with 1 bond. So if you guys have a pen and paper, let's go ahead and just kind of give me draw a rough representation of your isopropanol as shown, right? So there's a reason why I'm asking you to do this, all right? So doing it the Lewis bond structure way is the general method. But what I want to do is to kind of do a transformation. And what do I mean by that? So I could take this molecule and represent it in a different manner that looks like this, all right? So let's just do it this way. And this representation is referred to as a bond line structure, a bond line structure. So let's draw that nicely so you can see what I'm saying here, a bond line structure, right? So how did I make the transition? So let's just quickly label the carbons so you can see how I made the transition. So let's say this is carbons 1, this is carbons 2, this is carbons 3, this is carbons 1, 2, and 3. So we have 3 carbons. And the way we draw a bond line structure is that typically the hydrogens that are attached to the carbons are hidden, right? So remember, step 1, the hydrogens that are attached to carbons are hidden. That's the only thing we did. And then the carbons are just written as a dot, right? So instead of writing out C, we just put a dot for the carbons and connecting a carbon for carbon for carbon, and not carbon to an oxygen. So groups like oxygen attached to hydrogen are just condensed as OH. So what I'd like you guys to be able to do is to look at any Lewis structure and be able to convert your Lewis structure to what's referred to as a bond line structure. So here are the key things to note in doing this, all right? So remember we said that carbon is always tetravalent. It's always bonded to 4. If I pointed on this particular carbon and say, all right, on this carbon, how many hydrogens are attached? So I say, tell me the number of hydrogens are attached. And you may say, okay, how do I figure that out, right? And I'll kind of show you a clue how to do that. So remember, carbon is always tetravalent. So you want to look at what's to the right, what's to the left, what's next door. So if this is a carbon that's of interest, let me just use my highlighter to kind of guide the discussion here. So if this is a carbon of interest, you want to look at what's next door. So I know that I only have 1 bond, right? So 1 bond is already taken up. That leaves me with 3 other bonds. That means that I can assume that because 1 bond is already being utilized, there should be 3 hydrogens that is remaining that's attached to the carbon to make it tetravalent. And if I want to draw it out so it looks pretty and nice, I could do it this way as well to say that what we have before us is that we have a carbon that's bonded to 1, 2, and 3 hydrogen. It must always be attached to 4 bonds. If you jump to the adjacent carbon on the left, how many hydrogens are attached to the one in the middle? Carbon in the middle would only have 1 hydrogen attached to it. So we want to make sure that there's always like a 4 lines attached to a carbon. Even if you don't see the hydrogen physically, mentally, you should know that, hey, because carbon is tetravalent, I already have 3 bonds, so that means that the 4th bond must be attached to a hydrogen. And likewise, at the end, we know that the carbon is tetravalent, so there must be at least 3 other hydrogen attached to the terminal carbon. Okay, so here's a more elaborate structure. You guys are probably familiar with amoxicillin. So this is one of these nice antibiotic drugs, right? And you notice how large the structure is. It has a lot of carbons, it has nitrogens, it has oxygen, it has hydrogens, sulfur. So the time it would take us to draw this structure using a Lewis method would be time consuming. So the way to represent these antibiotics is just to convert them to what's referred to as a bond line structure. I'll show you how to do this. So if I go to the next slide, so we have the Lewis structure, and then remember the key thing is that if I give the Lewis structure, you should know by practice how to convert the Lewis structure to a bond line structure. way we do this is simply just for every carbon, we treat a carbon as a dot, and the hydrogens are all hidden except for hydrogens that are attached to heteroatoms like oxygens, nitrogen. So those are there. But all hydrogens that are attached to carbons are hidden. So if I do the conversion and draw the bond line structure, this is what it would look like. So take a minute, guys. Just kind of let that soak in for a second here. Just take a minute and let it soak in for a second. So notice that if you look at the aromatic ring on the left, each carbon is treated as a point, with a point for or a dot for each carbon. The hydrogens that are attached to the carbons are hidden, right? Only the hydrogens that are attached to heteroatoms like oxygens or nitrogens, those are shown, right? But everything else, hydrogens are hidden. So the goal for today is to be able to look at a bond line structure and quickly redraw that to make what's referred to as a bond line structure. So on the left side, remember that we have for every carbon, there's a hydrogen. Let's kind of draw it out. There's a hydrogen there. There's a hydrogen there. There's a hydrogen there. So for every carbon that has an end, we have a hydrogen attached to it, right? Is that good? So remember, what's important is that right where I've circled, there's no hydrogen attached to it. Do you see that? Where I put the circle, there's no hydrogen attached to it. And let me explain why that's so. So remember we said that carbon is always tetravalent. So if you look at the carbon right where you have the aromatic ring, you notice that the double bond constitutes two lines. So that's 1, 2 lines. The line go below, that's 3, and the line to the right, that's 4. So that's the reason why this carbon has no hydrogen attached to it. Check. If you go to the bottom where the hydroxyl group is attached, again, focusing on this carbon, it has 2 lines, so that's 1, 2 bonds. If you go to the left, that's the 3rd bond. If you go to the right bottom, that's the 4th bond. So that, again, this carbon has no hydrogen attached to it. And then we could go to the bottom carbon and let's repeat the same process. If we have 2 bonds, that's referred to as a double bond. That's to the right. And then we have a single bond to the left. So that's 2. And then to the left, that's 3. So it means that if I ask you how many hydrogens were attached to this carbon, because carbon already has 3 bonds, a double bond and a single bond, it means that there's 1 missing. So the 1 missing is just 1 hydrogen. So let's see if you guys have mastered the art. Let me just ask some questions. So now let's work backwards, all right? So let's look at the actual bond line structure. And what I'm going to ask is a very simple question, all right? So far, we went from the Lewis structure to the bond line structure. I showed you that carbon is tetravalent, right? So for every carbon, we could determine how many hydrogens are attached by just looking what's next door. Okay? So let's see if we can work this through together. How many hydrogens are attached to the carbon at the end highlighted in red? It is in fact 3. And let me show you why for persons who may not see this. So let me kind of erase the circle here. So remember we said carbon was tetravalent, right? So that means that if it's tetravalent, it's already attached to 1 bond to the left. So that means that it must have 3 other bonds. And these 3 other bonds must be bonds where hydrogens are attached to that particular carbon. Step 1 complete. All right, now let's keep going from right to left. So let's kind of move to the adjacent carbon. Let's circle this carbon in blue here. For the carbon that's labeled or circled blue, how many hydrogens are attached to it? So let's recap what we said. So first we said that for the carbons at the end, they had 3 hydrogens attached to them. For the ones at the end, right? They were actually, let me just label this, there's actually 0. Let's put a 0 there. It's actually 0 hydrogens attached to that carbon highlighted in blue. And the reason why is going back to the same rule, carbon is tetravalent, right? So if carbon is tetravalent, it just means that you want to look at the carbon and say, how many other atoms are attached? So if we look at the carbon in blue, there's one bond, there's two bonds, there's three bonds, there's four bonds. So this carbon is already attached to four bonds. So if it's attached to four bonds, it means that the tetravalence rule is satisfied. So there's no more room for an additional hydrogen. So if I circle the carbon in green below it, all right, can anyone say how many hydrogens are attached to this carbon highlighted in green? How many hydrogens are attached to this carbon? Because we already have three other bonds attached to that carbon, there's only room for only one bond remaining. So there's only one hydrogen attached to this particular carbon. All right, let's keep rolling. Okay, so let's keep going down. And what about this carbon? Let me circle the carbon right here. How many hydrogens are attached to the carbon that has a double bond to an oxygen and a single bond to an hydroxy group? There are none, because as I said before, we have exhausted the tetravalent rule. So that means that for this guy, there are no remaining space to add a hydrogen. So there are no hydrogen attached to this particular carbon. All right, let me jump over to the left side of the molecule. All right, so let me circle a carbon. Let's say we circle the carbon to the top left. How many hydrogens are attached to, right? So there's just one hydrogen that's available that can be attached. So the carbon already has three other bonds. It has a double bond on the right, it has a single bond on the left. So there's only room for one additional atom to make it tetravalent. So there's only one hydrogen attached to this carbon. Well, let's stick a one there. And then I'll just do two more and then we'll stop. So let's say the carbon circled back to the right. Oh, it only has one. And then the final one we will look at is, let's say we circle this guy here. Okay, so it has space to include another bond. As you said, for this guy, this would be like 0 here. This would be like a 1. This would be like a 1. This would be like a 1. This would be like a 0. So that's how I want you guys to take the time. Let's go through your textbook and just practice these examples, identifying the number of hydrogens attached in the bond line structure to the different carbons. All right.